Okay, so today we keep on going with the series of lectures on sparsity. I want to recap a couple of things we've seen in the last two classes to then move on and generalize quite a bit the ideas we introduced. So for us, sparsity so far has basically meant considering functions of this form, linear functions, where again we use this notation just as a proxy to linear combination of any parametric, finitely many features. Okay, so we just consider the linear model for the sake of simplicity, but any finite set of features would do. So again, anything I said works the same if I replace xj with some ij of x, okay, where I can have even more features than dimensions. In this setting, sparsity essentially means having L0 norm smaller than the dimension of the data. Okay, L0 norm is just a function that counts the number of components in a vector that are different from 0. So it's a very natural notion of sparsity. We've seen that this notion of sparsity, this norm, cannot be used directly as a regularizer because it gives rise to problems that are in general hard. And we consider a couple of different ways to try to find an approximate solution. We discussed greedy methods that I'm not going to go over again. They're kind of iterative, greedy techniques to try to find recursively approximate solutions. We discussed last time a bit more at length the case of convex relaxation by using the L1 norm, which is given by considering the minimization of the following problem. Replace the L0 norm with the L1 norm. The L1 norm is just the sum of the absolute value of the coefficient. So each coefficient counts not just whether it's different from 0 or not, but counts exactly its size. And then we penalize, in this case, the least squares with this norm. Okay? Again, this is a family of problems indexed over W. This is just a minimum over the W we are considering. And here, we just consider least squares, and this is the usual notation we've been using. This is the N by P data matrix, and this is the N by 1 vector of outputs. I'm dropping, just to ease the notation, the 1 over N normalization factor in there that should be there. Okay? We discussed a bit in which sense this is a good proxy of the L0 norm, why dropping the square that you would have if you consider the L2 norm is so important and makes such a big difference. And then we moved on to discuss a bit computations. Remember, we saw that we discussed a bit how to solve this. And if you remember, just to help me out here, we commented a bit on why this is not bad, but is also not completely trivial. It's not bad because this term is smooth and convex, and this term is convex, but it's not smooth. Okay? So it's not a bad problem compared to consider, if you were using this kind of regularization instead. Still, it's not obvious how to do this because this guy, again, is non-smooth. So gradient descent cannot be applied in its basic form. We said, okay, you could use subgradient methods, but we actually saw that one can get much better by exploiting the form of this. So what is special in this is not just a convex function, but is a convex function which is sum of two terms. Both convex, but one of them is differential. So this is the case where one can use so-called proximal methods or forward-backward splitting techniques. They basically reduce to the computation of something that looks a little bit like a projection gradient, a projected gradient, but where rather than a projection, we have to compute what is called the proximity operator. The iteration looks very much like, if you ignore this term for a minute, it looks very much like a gradient descent of the error term, just of the error term. Okay? And you see that there is a step size appearing that we choose exactly with the same rule you would choose gradient descent if lambda was 0. Okay? Which is what? You just go check the gradient, the norm of the gradient, or if you want the Hessian, and I just choose the step size according to that. In this case, the step size basically depends only on the error term. Okay? On this first term. The contribution of the second term is this so-called proximity operator. So these methods are called splitting methods because they do split the contribution in the two terms on the sum. So do you remember how the prox operator looked like? So it can be described component-wise. And it's what is sometimes called the thresholding operator. Remember how it looks like?
Between minus alpha and alpha and then minus.
Right. So in words, as I said from the alpha minus alpha alpha is check this guy in absolute value. If it's small, set it equal to 0. Okay? If it's not small, in principle, let it be. Turns out that you cannot really let it be if you're solving this, but you're just decreasing it or increasing it a bit. Okay? So the important bit here is to put the 0 here. Okay? If Wj is smaller than the threshold that you see here, that is, which depends on lambda. So it's kind of something that makes sense from an intuitive point of view. This is what I expect everybody. This one line here is what I expect everybody to remember: that there is something that depends on lambda and govern how many zeros are in my solution. That is what you want, and that's what makes sense. The rest is like the plus alpha minus alpha part that you're going to forget in a week anyway. And it's basically saying, if this is big, here you basically just have to remember that you do something slightly weird, which is when it's big, you decrease it a bit. When this is small, you increase it a bit. Okay? And again, this is the solution of this problem. Okay? This is what is called the soft thresholding operator. The first observation, again, is that this method splits the contribution of these two terms, the error term and the regularizer. The second observation is that it reduced to a very simple algorithm, an algorithm which is just a gradient descent with a simple pairwise computation that is essentially cost negligible with respect to gradient descent itself. And the old method just reduces to matrix vector multiplications. Okay, can I make these methods, can I try to accelerate these methods? Can I try to make it stochastic if I have a large-scale problem? Yes, you can do all that. Okay? So this is just a tipping point. But this is a good point just to appreciate that we learned a little bit of a new piece of information about optimization that seems to be relevant whenever you have the sum of two terms, which is both convex and one of them is also differentiable. Today we're going to see that, in fact, the same approach that led us there can lead to more general, to solve large classes of problems, and particularly problems that would have this kind of sparse inducing. Okay? Any questions about this? Again, the lambda is the one that you choose, and you have to do whatever you want to do, cross-validation or whatever you want. Gamma is just a step size that depends on this term. Now, one question that you should ask, so I'm going to ask you, and you can reply. What if I don't want to use the square loss? Can I use another loss function? He's saying as long as it is convex, it should not change too much.
It should also be smooth, right?
So that's an easy case, right? If it's convex, that's it. Well, what do you put in here? Okay. If it's convex and smooth, then it's really the same. You just replace this with the differential, the gradient of the loss function. Okay. And then gamma, you just have to go and check what is the bound on the Hessian or whatever is a good bound on the gradient, the norm of the gradient, and that's is non-smooth, then it might still be possible, but one has to think a bit, because in general it's going to be a complicated business, or a more complicated business. Okay, so in some sense, if convexity is like big deal here, but the fact that it's smooth is what really makes the whole thing simple. Okay, so this is one first comment. What we discussed the other time was also closing a bit this chapter about computation, was going back to the question of what is the price we pay when we replace this by that, okay? There must be something going on in the sense that we start from a problem that in general is hard, and now we replace it with something. So either we pay a price, or we must make some assumption that restrict the class of problems we're solving. And one of the reasons why this stuff has been so important is because conditions have been made. And the one that I described are the one for the particular simple situation where I'm dealing with a problem that looks like this. That I sketched last time are not the full-fledged learning scenario, but as kind of a simplified setting, where for the time being I assume my data to be, the input data to be fixed. I'm not sampling them, they're fixed. And for now I'm even assuming that I have no noise. So I'm basically considering a linear system, okay? And I ask a slightly simpler question than the usual learning theory question, which is there a regime, are there problems for which using L1 I can recover W star, where W star is one okay? So the question here are, if I don't tell you anything about this W star, I just tell you it's a generic vector, there's no way, if n is smaller than p, which is the kind of setting we care about, there is no way I can solve this problem exactly, right? I need to project it somehow, and then if I care about sparsity, there's no way, I can get if n is smaller than p, there's no hope to get the solution, I just have to project, okay? If now I tell you that I'm sparse, I'm giving you hope, because I'm basically saying that the effective number of degrees of freedom of the problem is less. And yet it remains to be seen if there is a range of values of n, p, and s that allow me to solve the problem exactly. Okay? The idea is qualitatively that we make this, but this should be something that depends on s. Okay? And in particular, if I were to tell you exactly where are the zeros, this would be exactly what you need. N bigger than the number of columns, because you go in, you erase all the columns that don't matter, and you actually get a system that is much smaller. It turns out that this is not enough, and something like this is enough. I put the p divided by s, but that's a bit too generous. In general, this, at least for a 1, this is the kind of guarantees you want. Again, what am I saying here? I'm saying, consider the zero norm solution of this problem. If you have this kind of condition, if you're looking for this kind of problems, then L1 are gonna provide an exact solution, okay? And there is also, typical condition we need is that the matrix X is actually not a generic matrix. It cannot be anything. For example, it's something like a matrix with Gaussian entries. Then I basically know that I'm solving L1 in place of and I don't pay a price. So on the one hand, this is very nice, okay? Because it gives a sharp quantitative answer to a question which is not obvious at all. It's something that you hope for, the fact that by making this sparsity assumption, you get something out of it. And here show that in the whole class of problems for which you can solve this under the determined linear system with no price at all, okay? Of course, now you can say, okay, can I add some noise? Yes, and you're going to have some robustness. Can you actually assume that this is a learning problem where the x are random? Yes, you can also go in that direction. But somewhat this is toy, the cartoon-like important take-home message of this story, that there is a whole set of problems for which things are fine. Okay?
Quick question, though. S is a parameter we choose, right? Yes.
Yes, so well, wait a minute. S here, so W star is a true solution. It's like the target, okay? There exists a solution. Then I'm going to try to produce a solution based on this convex problem that should find W star, okay? And actually should coincide with W star. So here, S is not a parameter that you choose, it's a parameter of the problem, okay? Saying, I'm lucky enough that I'm looking for a problem where the important function depends only on few, say 5 variables, and I've got 100 points in 1,000 dimensions. And I work with it. In practice, you will have to choose lambda, and I'm omitting a bit the details of how you set up the problem with lambda so that you can solve it. But this is just to give you a vague idea of what flavor of these results in this setting. And also somewhat to point at some of the shortcomings of this story.
Use in practice, like just check S log P and see if the one norm, or is there really like some constant?
There are constants. People have been working in the last 10 years to get this as sharp as possible. So they try to really get the best possible constants and so on. As long as you apply this to settings like these, where you have a linear system with a nice matrix, it seems to actually be tight. Okay, there are corresponding lower bounds and all. If you start to go in wilder, like learning scenario, where data are random, you don't know if they're Gaussian, you don't really know this guy anyway, there might be noise, it might not be Gaussian, then it's more of a qualitative message than an important predictive equation that you can use. Okay. In some sense, one point that one could start to ask, so what we want to do today is to basically take this whole story and move forward. Okay, and generalize it and asking ourselves, why do we want to generalize it in the first place? And we want to consider different kind of norms beyond the L1 norm. In particular, the ones I would like to discuss are the so-called elastic net norm. And then start discussing so-called structured sparsity. In particular, we're going to discuss group lasso. And group lasso when you have overlaps. Turns out that these are 2 examples, but actually cover a lot of different situations. And tomorrow we're going to make, Wednesday we're going to make a non-parametric, just discovering that is yet another extension of these 2 examples. Let's first fix something here and then move on to the structure sparsity case. You remember that at some point I show you this kind of situation, right? Kind of the picture we were making where we were saying, how come that L1 is sparse and the other one is not? And basically the idea here, if you just take a generic situation, you never get the kind of situation where you have a non-unique solution. Fair enough, let's think a second about it. And let's consider a kind of a, and when you see this assumption like this one, it's a kind of a stochastic assumption, but also very generic. It's a Gaussian is by definition something that is very isotropic. It doesn't like any direction in particular, okay? It's something that is stochastic in a very democratic sense. It likes everywhere in a random way, exactly the same way. And so in particular, if you were to really look at the W's generated by something like this for X that is Gaussian entries and Y that is like a Gaussian vector, you will definitely get something that in general might not be parallel to one of these axes. Okay, but let's see when that might happen. Okay, let's consider the kind of extreme situation where in your data you have 2 features that are perfectly dependent one to the other. Maybe you get the same measurements twice, or maybe there are just really, this is a physical process where you really have 2 things that somewhat, whenever this guy is activated, this guy is also activated. And you want to select, whether they're important or not. Suppose that they are important, okay? Then what do you do? Okay, there is a perfect correlation between the 2 of them, and this is perfectly reproducible. Now, if you take this so perfectly reproducible, it's kind of an extreme situation where you might also be able to take it out by hand. But in general, I think of a situation where they're close to be perfectly collinear, okay? So you can think that you start to get in a situation where this line can be arbitrarily close to be parallel to this, okay? And as soon as sort of error of any kind, you start to get instability, okay? If you want, this is a way to say, how come that L1 can actually recover the L0 solution? Well, you're making a solution that in some sense the L0 solution is well behaved. There are, what is called the viability condition. You're saying that the important variables can be recovered, okay? And so if you have, for example, two variables that you can completely swap between the other, they're completely identical, then it's quite clear how you can recover these guys, okay? At least how this can do, because you can basically say, I can take one, I can take the other, I can take combination of them, and then nothing will. Okay? So what I'm trying to, the take-home message I'm trying to provide you here is that while this seems like the situation where this generate situation over one seems very unlikely. If you think about it, it actually corresponds to a practical situation that happens because data are structured. They're not Gaussian. They're not generic like a Gaussian. They have a lot of structure inside. They look high-dimensional, but they're not. They have correlations and so on. So if you have important variables that do have correlation, you may actually hit the situation where L1 doesn't quite work. It basically starts to be unstable, starts to jump around. These algorithms start to not converge so fast because decided which one of the important variable would you want to pick. Okay? Does it make sense? But then you can ask, okay, how can I fix this? Okay. Notice that if you are considering something like an L2 norm, it doesn't matter. You can, in any position, it doesn't matter. He's going to pick the one you want. So one possibility is to actually consider what is called the elastic net norm, given by a convex combination of L1 and L2. Okay, so alpha here is parameter between 0 and 1. So this is the penalty I want to use. So if I am to write it here, I would write something like this. Alpha is, for now, I don't want to think about it as a regularization parameter, but just as a relative weight between the two norms. Okay, so there is a lambda outside, and then the penalty is a convex combination. Okay? Fair enough? Let's draw it. Let's draw what is the corresponding bigger. So how is this going to look like? You have to draw that. How is it going to look like? This side, the sleeping side. How is this going to look like? It's the sum of an L1 and L2. It's going to look like this. It's bumpy, okay, because there is an L2 contribution. But if you zoom in here, okay, if you take a look exactly what's happening there and you zoom in, you basically see that, and now it's going to be very hard for me to draw it. When you zoom in here, there is a kink. Because, you see, the sum of these two, is it differentiable or not? No, this guy contributes no differentiability. So differentiability stays there. So if you look in here, you do have a non-differentiability point. So there is a corner, okay? Pardon, it's not easy even when you are able to draw it, because your perception is that there is smoothness in there. But here there is really a corner. Right, so you kind of, and of course now you have that if alpha is very close to 1, the bumpiness goes away, and this looks arbitrarily close to L1, whereas if alpha goes towards 0, the corners start to disappear to the point that at some point it just looks like L2. You can start to think yourself, What do you think is going to happen when you use classic connector regularization? If you go back to our picture where you say, okay, I have a line here. Is it going to behave like L1 or L2? What is it going to do?
Isn't it that depending on if we rotate the thing well enough, so if we,
What do you want to rotate?
because otherwise we're going to fall on the smooth part. The angle is such
Wait, and stop there. So he's saying you already want to do strange stuff because you already decided that you're going to fall on the bumpy part. Okay? Is it obvious to everybody that's the only thing that's going to happen? They also just told you that you do have a corner. So why should you always hit on the bumpy part?
And if you want, this is the answer. You don't. The slope of this, you might hit here or here.
It must be the case, right? The of angles, depending on this alpha, you can play the game you want. You fix an alpha and you change the problems, or as it is more meaningful in practice, you do fix the problem, and you're going to have some amount of correlation among the columns, if you want, that fix an angle, and then this guy is telling you how you want to behave with respect to that. And he's saying what? He's basically saying, look, if you choose an alpha very close to 1, I'm going to do something and pick 1, okay, or any combination of them. I put myself exactly in the degenerate situation. Whereas if you put an alpha big enough, I'm just going to pick one of those like solutions. So what am I going to do? You basically have to write down this function. Again, suppose that you are exactly in a situation where you just have two variables, okay? And they are both important and they're perfectly correlated. A bit of a toy situation. You have to pick up just one solution, okay? And notice that that's exactly what you do because it's strongly convex. So there's just going to be a unique solution. So you have to decide how you want to put the weights. How you want to put the weights so that you have just one solution. Well, these two numbers, the two variables, we are assuming for this that they're just exactly the same. So you're repeating the same thing twice, okay? And how can you weight so that you only have one way to get one solution? Half weight to one variable and half weight to the other variable. Okay. You see what I'm saying? And suppose that you have W1 x1 plus W2 x2. Okay? And you want to write down this function, Wx. Want to write this thing out. Now I'm saying, okay, look, if you look at L1, it's going to try to look for a sparse solution. So if you decide that the numbers here have to sum up to value, it can put all the budget here and here 0. It can put also all the budget. Imagine that you put here is the same number, okay? Some value x naught. So L1 can decide to take this guy, okay, and discard this one, or the other, or any combination, because it doesn't matter. As long as the sum of the weights is what you want, which is the one norm that you fixed. L2 is going to do what? Really the same, he has to find the unique solution, okay? And by symmetry, there is only one way to form a unique solution, which is to put half the same amount of weight, half here and half there. Okay? So it's kind of a democratic sharing of weights among all the perfectly correlated variables. Okay? Does that make sense? Of course, now I'm just focusing on the two variables that are perfectly correlated. Then you can keep on going with all the others, right? So you basically, the point here that, qualitatively speaking, you have that this alpha is not really a regularization parameter. It's more like a parameter that you choose depending on the correlation among the variables, and it's your statement of what you want to consider correlated or not. Okay? You're basically saying the slope has something to do with correlation. It gets too close to 45 degrees, I want to call it correlation. And this is telling you what you call correlation. Okay? That's the basic idea. So is this something that you can cross-validate? Not really, because if you have two correlated variables, what do you want to do? You have to decide. Do you want to pick one variable or both? Okay? It's not a decision that the data for you. Suppose that you want to do, say, a computer vision. We said at the beginning that the reason to do sparsity are varying, right? One could be to just get very small models. And what do you want to do? Do you care about picking both variables, or you just want to pick one? Well, probably just picking one is fine. So forcing the algorithm to be as sparse as possible just by choosing a sparse solution is probably a good idea. But suppose that you want interpretability. Okay, for these variables mean something, and you want to understand all the ones that are important. Then what would you do? Probably this elastic net thing is going to be a better way, because whenever you have two variables that are important, the answer you can provide to whoever is asking you for the important factors is not. There is some important stuff, and I give you, but if they're correlated, I give you something. You can say, I give them all. Okay, if they're correlated, I'm going to pull them all up. Okay, that's the basic idea. So for interpretability, it seems that perhaps using something that is able to treat correlation inside is a good idea. And the one way to do this here is to basically pull everything up. When there are things that are important and they're correlated, I pull them up. Okay? Does that make sense? The important thing to know about this generalization of L1. In practice, this is used all the time. As you can imagine, this extra L2-like behavior gives you more stability. The problem becomes strongly convex. It's even hidden sometimes in solvers as a little bit of preconditioning to make things more stable. But if from just a pure modeling point of view, this is a new algorithm that, if you want, is able to treat correlation in a more controllable way.
Variables that have correlation measured by alpha, you're saying that then the solution will put equal weight on both of them? Always. Like you made this argument before that the only unique way by symmetry is to be half.
Yeah.
So once you pick alpha to set what you consider your measure of correlation, if two variables are that correlated, then they get equal weight in the solution.
Yeah, that would be the, again, this is the idea in the perfectly, so he's basically saying, once I fix alpha, I'm basically putting a threshold on the correlation I want to declare correlation, and then once I've done that, whatever falls in that group of correlated variables, I'm going to pick everything up with equal weights. The answer is yes, but also in kind of in a very idealized situation where everything is exactly identical. In practice, you never have exactly the same situation. But let's see how you can use it, for example, okay? You can imagine a situation which actually does happen in practice where you do the following. Alpha to be close to L1, okay? So do get a very sparse solution, okay? You initialize from 0, you try to get the sparsest solution, and you cross-validate lambda, okay? And then you have your solution with a certain small, big alpha, okay? An alpha close to 1, and say in the limit alpha equal to 1, okay? And then you cross-validate lambda. Suppose that now what you do is that you fix lambda and you decrease alpha, okay? You decrease your alpha. So you're saying, I allow correlation in, and I don't care as much about sparsity. I'm happy to get correlated stuff in. Suppose again that things are perfect, you're augmenting the range of perfect correlation a little bit. And what happens is basically that you start to, here you have more stuff going on, right? You have a situation where there were all these other stuff going on. Say at the first, and these two guys, the first two are perfectly, they're almost the same, but not quite exactly the same. So you did L1, and this guy, and L1 decided to take these two guys, okay? Now what you start to increase, you fix lambda, and you start to increase alpha, okay? Sorry, increase. Okay, so that you have some L2 behavior. What happens? That what you typically see happening is that there is a whole set of value for which you start to take this one weight, and remember, these two, again, were approximately the same, and you start to spread it on both of them, okay? Does the solution change? Well, we have to agree what we mean. Does the Wx change? No. I just decided to put two terms that I split in a different way. So doesn't change. What changes are the weights. Okay, in the first round I got, say, 0 and 4 for my weights because I asked for sparsity. At the second round I'm going to put 2, 2. Okay, when I declare these two things to be correlated, boom, I'm going to spread the weights equally between of them. Does this change? No, because this is the same number. Here I did 4 times this guy. Here I'm doing just the same thing, split it in 2 parts. The thing that is different is just the coefficient vector. Make sense? So in some sense, you have a grouping effect. You start to pull up things that are grouped together. Okay? Find these groups because you start to pull things up. But you do have this effect that you know that by pulling up alpha, you get correlated variables. Okay? This is the important part of this story because from the computational point of view, it's for free. Why? I want to solve that problem now, and I gave you this solver here. Can you recycle it? What do you have to do?
Move I want this to just do. You can just move the L2 component into the...
Right, you just say, let me go from a computational point of view, I'd rather put the L2 component here as the smooth part. Fine. And then it means that the only thing that's going to change is that in here, you're just going to get a different gradient, because now it's a regularized, it's kind of this regularized functional gradient. And when you compute gamma, you have to be careful because now it's also going to depend on this part here. But that's it, okay? We're not going to do it. You can do it. Maybe you are going to do it as an exercise, actually. But anyway, you can see that it's pretty straightforward. All right, so let me, yes.
Why do we have alpha and 1 minus alpha? That was not 2, well, actually, I guess it's the same. 2 meta parameters.
But it's a legitimate question, okay? I parameterize it this way. If you look at the original paper that proposed this, they actually just have 2 parameters, one here and one here, okay? And you just treat them as 2 different regularization. And this to me is a bit cleaner because it cannot explain what's going on. And it's basically alpha is a predefined user parameter on about what you decide to mean by correlation and how you want to deal with it, okay? And it basically says that, I want to deal with correlation by selective correlated variables up to a degree of correlation. This guy is the one that controls the trade-off between fitting and smoothing, okay? For any alpha, you can get, some kind of reasonable regularization scheme, but trading off the 2 things, and this one is defining the norm. Okay, so you could do actually the other way around, but to me this is a bit more informative of what's going on. Yes, of course, at some point you could say, okay, but what is the right level of correlation, or what is the most natural one? Can I set up some model selection criteria? You could, and then giving yourself that freedom. Again, the correlation is in the data, and that's how you want to fix it. So if you give yourself the freedom, then you could decide somewhat to cross-validate both. So let me make a few remarks, okay? So remark 1. Suppose that I have to actually use
This algorithmic parameters.
Then it means that I have to choose the regularization parameter alpha, lambda. And what I'm going to say doesn't really depend on elastic natural one. It can be either one. But it does depend on what I have to do. It does need to choose lambda in somehow. So what do you have to do? You have to run this for many values of lambda. You want to try to make it fast, okay? And every time you change lambda, you have to actually run a full iteration. How would you do that? Is there a natural order in which you do things? So you discretize lambda, you have a bunch of lambdas, small ones and big ones, and then you have that code. How do you use it? From using it once, okay? You can choose to use the big lambda or the small lambda. Which one do you think is going to be, when you run the iteration, you think it's going to converge faster in practice? Not because of any theoretical reason, just because you're thinking. It's going to converge faster if you put the big lambda or a small lambda? So you put very big lambda, you click and say solve this. If you put very big lambda, what's going to happen? It's going to say that everything is essentially almost ignore the data, okay? So it should be pretty fast. Just say, put everything 0 and just get out of here. If you put lambda extremely small, it's going to try to solve the linear. So intuitively should take more time, and it does, okay? So people use this basic observation at the beginning of what is called the warm restart or continuation method like procedure to train this when you have to compute the full regularization path. What is the idea? The idea is that, okay, you start from 0, and then the first thing you do is the W for lambda big. Okay? You get this new solution. Then you have to consider the next value of lambda, okay? So we are making it easy, and we just have true value for lambda. Lambda big, lambda medium, and lambda small. We decided that from a computational point of view, it seems faster to start here. Okay, now you have to consider this guy. What you're going to do? Okay. You start from 0 again, you put lambda medium, and then you see what happens. Or, what do? To initialize this, rather than starting from 0, you start from, surprise, this guy. You hope that they're going to be close enough, and these are going to be a bit closer to the one you're trying than 0. Okay, why should it be 0? So you basically initialize this procedure with lambda med, and you get this lambda medium, and you keep on going. Okay, so that's the basic idea. Instead of starting from 0, you warm start your iteration with the one that you just computed. And this way, if you use this, if you don't do this in practice, this is insane. Okay, if you really have to go run this iteration. For every lambda, it takes forever. You have a fast algorithm. If you do this trick, it's going to be manageable. Okay, it might not be the faster thing, but it's manageable. You still have to put a problem with memory, but it's definitely manageable. If you don't do this thing gets quite useless. So I'm mentioning this because it's quite important. Is this clear? Yep.
So can you do the other way? Except when you do small and you find some things at 0, just throw away those features and then go down and then do the medium and then just throw away more features and then...
Yeah, you could. So what he's asking is, can you do the other way around? So the other way around would be kind of a, basically, so all these are hacks, okay? They don't come with particular guarantees of not doing crazy stuff. This one is basically the one that goes in and say, I'm going to start to put a lot of zeros and then few non-zeros, and then I go and recompute what's going on. He's basically saying, let's go the other way around. What is the problem of going the other way around? Because at the beginning, you're going to put lambda very small, which means that you're going to get most of your vector, you're going to have non-zero entries, right? So if you don't say anything intelligent now, then there is no reason to go that direction, but he's saying something intelligent, which is saying, okay, but maybe I find out that 5 variables are not important, I throw them away. So when I go from here to here, I'm actually consider a reduced problem. If you can ensure that as lambda increases or decreases, the set of variables that you select are nested, then it would be fine, right? Suppose that on the other hand, what happens is that once you throw away the 4 variables here, if you actually kept them in, they would have kept here because you discover some kind of multivariate effect. Then that would be a bad idea. You see what I'm saying? Here you're saying, say the first, when you only give, if you ask me to keep all of them, I throw away these 2, okay? Then I put a slightly smaller one, slightly bigger one, and I start to select more. And I say, no, I like to keep them because now I do see some effect that I didn't see before and keep on going. It's conceivable that this stuff happens, and I'm not in position to give you any particular insights. I think both are fine. This to me is kind of the standard one that people do use. In some sense, is the simplest one.
There are indeed multivariable effects. Then, like, doing warm start in this direction will be kind of biasing it towards, like...
Yeah, but you can still recover from it. Once you take, because I'm not... So the difference between the warm restart this way or your elimination strategy is that I'm always allowing every lambda to see all the variables. So it might take them a while to recover, but they could, okay? And in practice, you can check what's going on. If you take them away from the game, from this guy just doesn't see the first few, so there's no way he can recover. So in some sense, the one I proposed, I described first, is a bit safer, okay? But definitely things have been trying. So the idea of trying to throw away variables along the way to reduce the size of computation is tempting, and people have been trying a lot of ideas in this direction. This is just one trick that is super important in this case. The other thing which is kind of important is the fact that hardly ever people do just this. So especially when you do statistical problems like in machine learning, it turns out that this is annoying. It is really annoying. And the W you get, you can trust the fact that it's not different from 0, but you can hardly ever trust this number. Okay? Because you're basically saying, exactly what you're doing is that you are creating a bias. So say this guy should be 4, but I make it 3. Okay? So what happens? Again, suppose that in this case I would like to put weights. This doesn't matter. We can do it for, these two are different, okay? It doesn't matter. I would like to put weight 4. There is only one variable that matters, and the weight is 4, okay? But it so happened that my algorithm, because I kind of stink in that respect, puts here a 3. Then I don't get a very good solution. So what is the algorithm going to try to do? Look for the next best variable that can, contribute something, and put a little weight there, okay? 1. Okay? So what happens? Because of this effect, if you care about finding the solution, you may actually get less sparsity than what is actually in the problem because of this computational effect. What do people do? They don't use this one-step procedure. They use a two-step procedure. They basically say, I do believe this as a selector, okay? But then I want to run simple least squares on the selected variables and to recompute the coefficients. Okay? So we typically do like this. So this is sometimes called the bias step. You basically do L1 and then ordinary least square on selected variables. You see what I mean? I'm basically saying you put a certain lambda, you find out that it gives you 4 variables. Okay? Then you use those 4 variables and recompute the coefficients. You take a bigger lambda, and then it gives you 2 variables. You take the 2 variables and recompute the coefficients. It might be that once you recompute them, 2 are enough. Because in this case, for example, I did just L1, and it gave me this solution, because it could not put a 4 here. Okay? Now, and this is for lambda medium. Okay? Now I put a lambda big. Okay? It gives me just something different from 0 here. Okay? Not the right number, but at least it gave me only 1. But then I'm going to go in and recompute this anyway. Okay? So I'm going to put the right numbers here. And this says, no, you should put 4. Okay? So now what you see is that if I use this two-step procedure, I use this as a selector, and then I use least squares on top of it as a recomputing the coefficients, we see more sparsity in a way. And again, this is more of a practical insight. But it's hardly ever the case that when you see this stuff applied, you don't have this step. Okay? Essentially because while asymptoticity will not matter, in practice it does. Okay? So at least these two tricks are tricks that I know are used all the time when you use this. Otherwise, you don't manage to make them really work. Okay? And there are a few more, but at least these 2 are actually very important in practice. You do one restart when you have to compute multiple lambdas to make this manageable, and then you do this second step. And in practice, the second step might be more complicated than that, because maybe squares is not good enough, maybe you have some extra regularization, blah, blah, blah. But this is the basic idea to at least start to go and look this kind of stuff if you need to use them in practice. There have been also an attempt to try to understand a bit more theoretically both these things.
Or just this?
For us right now are just pointers. So the few comments are let's go beyond L1. Let's try to look at what happens when you have correlations. Let's introduce elastic net and get a feeling of what's going on. From a computational point of view, not much. From a modeling point of view, you can get this intuition that you're dealing more explicitly with the presence of correlation. And then it's just a very a couple of very quick computational, useful remarks in practice about warm restart and about the biasing after you selected variables. A small question to you is, that thing I wrote, the L1, the elastic net, they look a little bit like something else. What? If I show you this plot, and I don't tell you how I got it, and you appreciate how badly I usually draw. This thing looks like what? Rather than, it's something between L1 and L2. So it feels like it might be something like an LP norm. What is the difference between elastic net and LP norm? So if you do an LP norm, okay, and I choose P between 1 and 2, it's going to look pretty much like this, right? It's going to be a norm that looks like this. When I say P norm is because I always call it like this. We have to call it the Q norm because I call the variables P. Okay. So this is the norm, and I want to take Q to be 3/2. Okay, it's going to look something like that. What is the difference between that and elastic net? There is no key. Okay, this is smooth. And in practice, at least in principle, you have reason to believe that this is going to give you any sparsity at all. When Q is bigger than 1, okay? More than 1, then you're back to the concave setting. There's no reason to believe what we said, right? There are some results that actually do suggest that if Q is small enough, you can still see some form of sparsity. But at least in principle, this is the macroscopic difference between these two.
Yeah. You said that in certain circumstances that L1 become unstable. If you look at the way you solve this, the proximal operator, adding the regularization, since we're doing gradient descent, will not make the matrix invertible. Like the Tikhonov allowed us to invert a matrix.
We're not inverting a matrix.
That's exactly what I'm saying. So in this case, that means that I don't see why suddenly adding a little lambda there, it makes it stable because we're doing gradient descent resting stability.
Okay, that was kind of a qualitative statement, but you can actually see it in at least two different ways. One is just a pure geometric point of view, not considering the iteration, but just as the minimization problem. And the idea is just that if you're in a situation where this is close to be 45 degrees, you can jump here or there or here or there, depending on small perturbation, okay? You can do just a toy example and convince yourself. So in that sense, it's unstable. Whereas if you make this fat, boom. Instead of moving from here to here, it's going to move from here to here. So that's just one simple intuition. Okay? As long as I put a little L2, I make this wide, and so rather than jumping around like crazy, it's just going to jump. This is one way to see it. Not looking at the iteration, but just looking at the minimization problem itself from a geometric point of view. The other point of view is what about the iteration? And there, forgetting about this, you just see that you're preconditioning the problem. This problem here, if you put alpha equal to 1, is convex, but not strongly convex. And so if you look at the curvature of this, which is something that typically controls the rates of convergence, you're going to get like a bad case where you can have flat regions. It's something that is like a smile with flat regions. But if you put this, it becomes strongly convex. And we know from, for example, in gradient descent, you move from sublinear to linear rates, or from polynomial to exponential rate of convergence. And for this algorithm, you actually have exactly the same behavior. As long as it's strongly convex, boom, you go super fast. But this is another point of view where, in some sense, you forget about L1 is a generic statement about the fact that I took an optimization problem and I added a small strongly convex term, so I make it much more curvy and so much better conditioned. Okay, so these are two possible ways of seeing in which sense L1 is more unstable than L2. One is more modeling, one is more computation. Okay. All right. right, so the story about elastic net also pointed in a direction which is kind of different, and is the idea that there might be more than sparsity in the trivial sense in which we just say, look, this is what's going on. Okay, so far this has been sparsity. Like this, there is a lot of nice idea, but this is somewhat a specific way of considering the sentence. There are few important building blocks, okay? Because we identify building blocks with individual variables. When you talk about structure sparsity, you question this very correspondence. You keep the general statement. It's a problem where there are few building blocks, but you question what are the building blocks. One possible situation is to go away from something like this and consider the situation where, suppose that this is your vector of variables. This is your W. These are all its components. We start to say, we introduce a different notion of building blocks. We say that there are groups. Groups are not something you learn, it's something that you're given. I tell you that these variables are divided in groups. Each of these is a variable, and then you have three groups, okay? G1, G2, G3. Okay? They're given. Maybe a situation where, for example, you have biological processes where you know that the variables that are involved in a biological process are all also connected to some bigger. So all certain measurements you do are involved in the same biological process. So you can think of this as a biological process, this is another one, this is another one, and you know that they go in groups. And what you try to select or suppress are not individual variables, but these kind of biological processes that are described by each of these groups. Okay? All right, so can we design a regularization term? Exploit this assumption. This is the kind of game we want to play for a couple of times now. Okay, we do have L2, we do have L1. We have this idea, we have a bunch of ideas. We have this idea of relaxation. We have these proximal methods. We now come up with different priors. Okay, different priors than L2, and they are not really described in terms of smoothness. They're more like about building blocks. And we want to come up with ways to design models and get a feeling of what the hell we're doing. The first case is this. Okay, it's simple, but it's already a step in a more general direction. Okay, if you go in the specific case where the groups are every one of size 1, it reduces to the usual L1, but in general it can be different. Again, the key point here, I'm not trying to select individual variables, but groups. How can you design a regularization to do this? Well, L1 or L2 are not going to do it, right? What they do is that they're going to, one is just going to try to do smooth stuff, you know, a complete body. The other one is going to try to kill each one of them. This one, no. In some sense, I want to do something like an L1 on each group. How do I say an L1 on each group?
Together, and so it becomes a big factor and take L1 over factor.
Right, so let's take what's good in what he said and at least a 1 degree of freedom I want to fix is basically saying, let's take all these and let's make them into one number, okay? Once you have one number, you can actually go into L1 on that one number, okay? His proposal is to actually take all these numbers and multiply them. But one other thing you could do is to actually take all this guy and do the norm of this vector, okay? So that's what we want to do because it turns out to be the thing that is typically done. So I need a bit of notation here, okay? And if you give me a W, okay, and now you give me the part of W that corresponds to a group, I want to call them W1, W2, W3, okay? So when you see W with parentheses, it means that it's a W which is not of the same size of this, is going to be of the size of the group. Okay, is R2 the cardinality of group 1. Okay, you just take how many elements you have. So it's a shorter vector. And what he's saying is that I want to, in some sense, have a way to collapse all those values of that vector in each of these groups should count one number rather than all the variables in the group. The typical choice that is done is this. You take W and you map it in something that is like this. I'm just going to do the case with 3 just for the sake of simplicity. Okay? So you do W1, W2, W3. So you do collapse them, but by taking the norm, not squared, and this is going to matter. You're going to tell me in a second. And then what do you do? Now, this is the guy you want to use for whatever he said, which is taking now the sum of this guy. So I want to take the L1 norm of this vector, which is just the sum of the norm from G to 1 to G. Okay? Here, this is our proposal. We want to take here G. It goes from 1 to non-calligraphic G. This is the total number of groups. Then I sum the norms of this shrinked version of this vector. Okay? This is what is called, sometimes it's called an L2, L1 norm. Because you do an L2 and an L1 norm. Make sense? Okay, let's rewrite this guy. Okay, this is what is sum of, the notation becomes a bit annoying. J square square root. J goes from 1 to the number of elements in the group G. Okay, it's a bit annoying, so let me just reread it. This norm here is the norm, if you want, in R G. Okay, is the vector of the size of the group. And each of them can be of different size. I'm not saying anything about the fact that they have to have the same size. So here I just have to go in and write the usual L2 norm. So what you see basically is that you, very similar to L2, you're actually going to take the square of every coefficient in this vector. But very differently from L2, you're going to trap every set of values that correspond to a group inside a sum and a square root. So the square root is very important. Okay? If you were to just do this, say, it will just be L2. Okay? I take the square root away, it's just the sum of the squares. I just split the sum into one big sum in two sums, but it doesn't matter. So the square root is basically saying, no, I trap all the elements into a group in the same one. Okay? So, and again, these are just words to make this a bit easier to remember. Yes?
Apply with the L1, like if you just add up all the L1, wouldn't that just be the L1?
This one?
Yeah.
But who's similar to the one? So if you, but let me finish the comment so we see. So if you take away the square root, okay, is exactly L2. You agree? If you move the square root inside, then it's exactly like L1. Okay? If instead of the square root of the sum, you take the sum of the square roots, then you're basically just killing the square. Okay? And then it becomes just L1. But if you keep the square root outside of the sum over each group, again,
That line, right? Lambda sum of G equal to 1. No, the line above. There, yeah, isn't that just L1?
for you at this point, because I don't know how else to. This is equal to this. Okay? I just rewrote it. Now above I rewrote in a different way. Okay? So I just rewrote it here, where this norm is this R to the G, and this is what I wrote above. Okay? So, and what I'm saying is the L2 norm? No, because this is the square root. Is this just L1 norm? No, because the square root is not inside of the sum, it's outside of the sum of each group, so no, okay? In some sense, I use this, just to, in some sense, this square root is something that groups. Is the grouping effect comes from that, exactly from that square root. It's very, okay? If you don't put that, you just boil down to one of the usual ones. Make sense? Yep.
So why L2 as opposed to LP, or even just like adding them up and then taking the absolute value of the sum afterwards?
Good point. Good point. So once you see that you have L2, L1, clearly an important bit is the second L1, because that's what is going to kill the group. The effect on the, inside L1, on the L2, I mean, the way you reduced, even he said even something else, okay? You can do different stuff. We're going to do this just because this makes actually computation easier, as you can remember, because this become a particular simple thing because it's just an L2 norm like projection. If you do more complicated stuff, which you have to argue what is the benefit from a computational point of view, you would have to do more complicated computation. In this case, I can just show you the computation, but definitely that's a direction of where people have been going. L1, L2, and then you can start to say, I question L1, LQ, okay? Or I can do also start to question to see what happens, and I start to elastic net here and there. Yes, people have been doing structure sparsity for 10 years because the combination are actually many, many, many. But this is the basic idea, okay? And exactly this question that we are discussing now, the comparison with these two guys are what makes you, get your feeling of what the hell you're doing. Okay. Far so good? Now, as you can imagine, we could spend some time doing some drawings, okay? Drawings of balls in more dimension and try to understand what's going on. We're not going to do it, okay? The rough idea is that you can see these as a proxy L0 norm of this vector here and try to develop a theory and keep on going, and you expect that if things are right in the theorem that I sketched before, the one where I had the number of points that should be proportional to the L0 norm, in this case will be the L0 norm of the group and so on and so forth. So again, this is by no means an extensive display of all the possible results, but you can kind of see what's going on. Once you have this idea in mind, you can kind of see what's going on and how you're probably what the kind of question you want to ask next, okay, about sparsity. The one I want to show you is just the way this proxy is going to look like. If he put this stuff, okay, so let me call this norm the group lasso. This is what is called the group lasso. I think if I told you or not, but L1 regularization is actually called typically either basis pursuit in signal processing or lasso, which is an acronym for something, in statistics. And this is a lasso, an L1 penalty with groups, okay? So this is called the group lasso. And so the next question we want to ask is, can we solve this efficiently? Can we use proximal methods? Can we compute, and then the question is going to be, can we compute the proximity operator in a nice way? We had the soft thresholding before. What do we have? Okay, this is the question we want to ask. You got a question? You don't, you're given. I'm assuming them to be given now. Okay, and a good question is, what if you're not? For now, we're just assuming that they're given. Maybe you do a pre-processing, maybe you do some kind of clustering, whatever. It's a big, missing big, bit in this whole story. But for now, I'm just saying, if you know them, with elastic net, you were trying to some extent to find them, okay? Here, you assume they're given, and that's all. So we're not going to comment on the statistical project or anything here. You're just going to get the idea that this must extend the discussion we had for L1, L0. What about computations? That we want to take a look at, because it's something that is actually, yet again, giving you a good idea of this proximity operator are useful in this context, because it looks exactly like you would like it to look at. So, I want to give you the proximity operator that corresponds to this norm now, okay? Spoiler of what it's actually going to do, it's actually called the Brock thresholding operator. Okay? Because it does what? He looks at the group and does a thresholding not on each individual variable, but on the norm of that group. Okay. To describe what he does, again, I'm going to do it for a generic alpha we did before. Okay. Before, when I put here the L1 norm, to describe the action, I have to describe the action on each variable, right? Here, actually, I have to describe the action on each group. So you're going to have a prox. It decomposes nicely. It becomes the prox on say, the first group, prox Okay, what did I write? I just write that the prox of this stuff here decomposes nicely in the concatenation of the prox of each term in this. Each of these terms is just an L2 norm, and then what I have to do is I have to do this prox of each of these guys. So now I have to tell you how this looks like, okay? I have to tell you what prox alpha norm W looks like, and I'm going to do it in components. Okay, yes.
The gradient descent inside the prox.
What about it? Sorry.
Where did it go in your new block threshold? Because when you like do on a single term, then you like do the proximity on top of like the whole weight vectors, and you do it component wise.
Yes.
But in this case, it's in a block thresholding. So where's the weight vector of the?
So the question is,
I have a proximity operator that acts on a gradient. Let's see how it acts. Okay. So the gradient descent is going to spit out a vector, which is of the size of the number of variables, right? Now I'm telling you what you have to do with it, which is take the vector, split it in its blocks, okay? And now let me tell you what I'm going to do with each block. So if this is 10 variables, say it's 12 variables, and this is 4, 4, and 4, I'm going to take 4 variables here, and then I have to tell you what I do here. And that's what I'm going to write next. Make sense? So what do you do? Well, if I were to do the soft thresholding, I would look at, say, Wj, but here I actually look at the norm of Wj, okay? So, sorry. So here I put, again, let me tell you what happens if you consider the gth group, okay? If you consider the gth group is a vector of size rg, blah, 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 then you have to consider this norm, which again, a bit in a pedantic way, but we use the notation, so now you get it. I check if this norm, the norm of the group, is smaller than alpha. If the group is smaller than alpha, I set every coefficient. You see, this is a component-wise thing. So I set every coefficient in that group to be 0. So to set the coefficient to 0, it's not that its specific coefficient has to be 0, but it's that the sum of all of them have to be small enough. If the norm is bigger than alpha, size can be broken arbitrarily here, then what you do is that you take the Wj, j, the jth component, and you subtract alpha Wj divided by the norm. Okay. So read it and tell me all the mistake I make, where I write what I. Again, the block operator is the prox operator is just the concatenation of one operator per block, and each what it does is that it goes in, compute the norm of the block, the group, and check if it's small or not. If it's small, you set every coefficient to 0. If it's not so small, depending on the value, it actually does a shrinking that now depends on the size of this norm. Okay, you can actually rewrite L1 exactly in this way because if you just take the specific case of each group of size 1, we just go back to the usual L1. They just collapse one to the other. Okay. So again, the derivation of the iterative soft-thresholding is an exercise that you can basically do with elementary tools. This requires a little more work, but not too much. Okay. Yet again, what you see is the power of this forward-backward splitting and proximal operator techniques, because this is yet another example where the algorithm is remarkably simple, right? It's a bit annoying to write, and mostly it's because I have this group stuff, but you can imagine, once you have arrays in your, it's super easy, and all you have to do is a gradient descent, and then a simple. Again, you can say, okay, but then I make it faster, blah, 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 blah.
There was no mistake.
So let me tell you what we want to do next time, okay? And then we stop here. The limitation. Okay, we discussed L1, then we discussed a bit how to go between L1, beyond L1, continuous elastic net, thinking about correlation or structure. Here we're still thinking about structure, and the structure is going to be something that is now given as a prior, and you want to try to exploit it, incorporate it, okay? And we start from this basic situation where you have groups. This is the first step. How can you make this more general? What is the one assumption that we made here? That it's kind of annoying.
They're all disjoint.
Yeah, the groups were all disjoint, okay? I mean, we made the assumption that it's the square loss, but as you can imagine, in for differentiable stuff, we took L2L1, and yes, you can consider L2L1. But the one assumption that we made that seems to stand out is that the very first line I said, you have groups and they don't overlap. So the next question is, okay, but what if they do overlap? What if I have a situation where this is group 1, this is group 2, and this is group 3? How do you deal with the overlap? Okay? That's a basic question we want to ask. And this is important because once you know how to deal with that, you can consider now, when you allow yourself overlaps, you can do a lot of stuff. Because, for example, you can say that your variables are divided in groups, they are themselves divided in groups, they are themselves divided in groups, and they form a graph or a tree or something that you know. Okay? And you might have a situation where this structure is available or you pre-learn it somehow and you can try to use it. Right now, by making this, we're simplifying things a lot in general, but once you go to the overlapping case, you can generalize things a lot. So what we want to try to do next time is to do this, and then we're going to do the following thing. You see, each of these groups has finitely many elements. We will never be able, at least in our formulation, to consider infinitely many groups, but what I think we're going to ask is if we can make each group is infinite dimensional. Can we view each of these groups as a feature map and viewing each group as a concatenation of three feature maps? Because if you could do it, maybe we could do something where you use different kernels, okay? Instead of one kernel, we're going to use different kernels and combine them in some kind of sparse way. Whenever you say group, I'm going to say kernel. Say group, say kernel. Say group. That's what we're going to do on Wednesday.